Okay, I guess we can get started. So today we are going to talk about spatial analysis. So it was the sampling, but I think after tomorrow's field sampling, like when we have the real experience, I think that will be better to talk about that after the lab. So this lecture is more about the theory. So first, I would like to talk about correlation and how to calculate the correlation. And then correlation can be evolved in spatial analysis. So I will talk about a little bit about their relations. And then I will talk about correlation and covariance. So they are frequently used in spatial analysis. And then I will just jump to how to interpolate the spatial data. And then I will especially focus on the deterministic spatial interpolation method. And then I will be talking about the statistical spatial interpolation methods that will use the correlation and covariance that they have been constructed. And so first, let's look at variance and covariance. We are very familiar with variance. So basically, variance is a measure of dispersion. So, and the equation of variance is like this. But note that here I use n because this is the population variance. For the sample variance, it equals to n minus 1. And then we have the same thing here. And for the covariance, I think covariance is less commonly discussed in statistical lectures. So covariance is a measure of how much two random variables vary together. And the definition of covariance is like this one. So the purpose of showing the formula of variance, because we can see that their shape are pretty similar. And we can see covariance of variance actually equals to the covariance with x and x. So basically, if we replace this y into x, then covariance will become variance. So we can see that variance is a special case of covariance under the condition when x and y, they are the same thing. And the formula of covariance is this. And by knowing this formula, we can do the calculations. Let's start taking notes. So let's look at more about covariance. So this is definition, and intuitively we can see that on the left side, covariance, like the value of covariance, it can reflect the relation between two variables. For example, for this data, we can see they are kind of positively correlated, and the covariance is positive and it is relatively large. And for this one, it is 0. And for this data set, they are kind of negatively correlated, and the covariance is negative. And same for this one. So again, covariance is a measure of how two variables vary together. And for the calculation, here I just show an example. So suppose we have two sets of data, x and y. But note that when we are calculating variance or covariance, same like the linear regression, the data of x and y, they are coupled. So in this case, first we can calculate the mean x and the sample mean and the sample mean of x and the sample mean of y. So we can calculate them first. And then we can calculate the sample, the number of the sample minus sample mean of x and y separately. So we can have these two columns. And then we calculate the cross product of this part. So we can have the column here. And finally, we want to calculate the average of the sum of the average of this column. So we can calculate the average of this column. And this is a covariance of this data, we can see the covariance is positive and it is about 100. So for this one, do you guys have any questions? No. So you guys can just try to reconstruct this table by yourself. So you may be more familiar with this one. Yes.
Do we talk about covariance in relation to samples or only population?
Yes, that's a good question. So based on the formula of covariance, we can see that it uses n. So basically, I would say I did some research because I also had this question about this. And when people are talking about the sample covariance, I think they also use this one. And I think the reason is that when we are calculating the covariance of two data sets, the number of data, the sample size is really a little bit large. So the difference between n-1 and n, the difference between these two values, they are not quite different. But I mean, in this case, they have relatively small sample size. But in many of the other cases, like this ones, we can see the sample size is relatively large. So I would say when we are talking about covariance, we do not differentiate sample covariance or population covariance. We just consider them as one value. Yes.
Is there a correlation between covariance and a regression value?
Yes, I will talk about this later. That's a good question. Any more questions? No. So if you guys have questions, you guys can post your questions in the chat. So, but covariance have a critical issue that covariance can be infinitely large or small, and it depends on the magnitude of the data. So we cannot compare data, we cannot cross-compare data from different things. So it is hard to make a standard. So correlation coefficient, I think, is more frequently used to describe the relation between two variables. And so basically the covariance is a normalized variance. And how to do the normalization? We can just focus on the left part. So correlation coefficient is defined as R, and it equals to the covariance divided by this part. So this part is a normalization factor, and this is the variance of X and variance of Y. And in other words, because we know the variance is the square of standard deviation, so it's also equals to the covariance of X and Y divided by the standard deviation of X and the standard deviation of Y. So the standard deviation, the product of the standard deviations are the normalization factor. And then we can do some of the mathematical deviations, which is not the focus of this class. I show this just for the sake of integrity. And finally, we can get this equation. For this equation, we can, as we remember when we are doing a linear regression, we have defined like X bar, Y bar. This should be X bar and Y bar. Again, I think this is a display issue. And again, we have SX, X, S, Y, Y, and SX, Y, which we have been familiar with. So we can just replace these definitions to here, and we can find some similarities. And finally, we can have this relation. The correlation coefficient equals to SXY divided by square root of SXX times the square root of XYY. Yeah, this is a little bit hard to read, but so here we have two methods to calculate correlation coefficient. The first method is to calculate covariance first and calculate the standard deviation of the sample. And again, I was also confused about, shall we use the sample standard deviation or shall we use the population standard deviation? But based on the deviation, we can see we have n here. In other words, we are going to use population standard deviation instead of sample standard deviation. And another method is to use this one. So we can calculate the correlation coefficient directly from like this axis. And here is an example. So this example shows the second approach. So we know the formula of correlation coefficients, and we know how to calculate SXX, SYY, and SXY. Again, we have the same data set. So first step, we calculate mu X and mu Y. We calculate here. And then we calculate Xi minus mu X. And we can have the column here. And we can calculate the square of each one. Then we calculate Yi minus minus the mean of Y. So it's here. And we calculate the square of them. And finally, we calculate the average of the cross products. So we can calculate the cross products of each one, and then we can calculate the average of SXY. I think, so this is the sum of SXY. I guess I need to calculate average, but I calculated the sum. But anyway, so this is the sum, and then we use this divided by the sample size. Wait a minute. Oh, yeah, I'm correct. So this is that one. So this is SXY. Yeah, I confused myself. And by having SXX, SYY, and SXY, we can just plug these numbers into this formula, and then we can get the correlation coefficient. So for this one, do you guys have any questions? Except for the question about correlation between correlation coefficient and the linear regression. I will talk about this in the next slide. And any more other questions? No? Yeah, again, I recommend you guys to reconstruct this table. Oh, that will be the next slide, not this slide. This slide is talking about the properties of correlation coefficients. So based on its definition, and we can see that SXY, the square, is smaller than the products of these two. So in other words, the correlation coefficient is in this range. So it is greater or equal to -1, and it is smaller or equal to +1. And its values shows different meanings, which I think you guys are familiar with this. So when the correlation coefficient or small r is -1, which means they are perfectly correlated, and their correlation is like they are negatively correlated. And if it is equals to 1, then they are perfectly positive correlated. And for different values, it represents different extent of correlation. And if we want to describe this correlation, we may use some like descriptive words. Like here, I just take this table from a paper, and it shows that if we have different values of correlation coefficients, then we can use different verb to describe. But again, I would say that when we are reporting the correlation between or correlation coefficients between two variables, it same as the hardness. It would be better to describe, like to have this interpretation first, but as well, we need to provide the number of the correlation coefficients. So we can provide these two information together to make it more accurate. Again, so in practice, it is also good to report our values and the description. On the other hand, I also want to mention that in the scientific research, we often want to know if the R, the correlation coefficient, is significantly different from 0. Say if at P is smaller than this one. So in this one, we may say their correlation is significant or not significant, which is similar to t-test. And we may have two interesting situations. We may have low but significant correlation, like the correlation coefficient is 0.01, but it is significantly greater than 0, which means the correlation is small or weak, but this correlation is significant. On the other hand, we may also have the situation like we may have very high correlation or very large correlation, but this correlation is insignificant. So this seems a little bit contradict, but they can exist. And we need to be cautious about that. And so for this one, do you guys have any questions? Nope. The internet connection is unstable. Let me just do a quick check. Okay, I have internet. Okay. And the next slide is about the correlation between correlation coefficients and linear regression. So first, when we have the question, because for the linear regression, we have this R square, which is coefficient of determination. And what are the relation between correlation coefficients and this R square? Actually, they like R, small r equals to the positive square root of this big R square. And on the other hand, we may also have this relation. So correlation coefficient and the regression coefficient of B. So we know that B is a slope. We know that R equals to this one, and we know B equals to this one. After some replacement, we can have this relation. This relation tells us that the correlation coefficient is in positive proportional to the slope. And we know that this part must be positive. So like they are positively related. And on the right side, I just show an numerical example. So again, we have the same data set and we can do the linear regression and we have the R square equals to this value. And we have already calculated the small r of this data set. Then we want to evaluate if the square root of this one equals to this one. And we can calculate the square root of this big R square. It equals to this one at this accuracy. Yes.
Do we know how to calculate big R squared, or is that just from Excel?
Oh yeah, I didn't mention about how to calculate this big R squares in this class. And yes, you can find this on the Excel. And I will not ask you guys to calculate this big R square like by hand. I may ask you guys to calculate the big R square by using Excel or other softwares. Yes. So any more questions?
Yeah. So which one do we prefer to use?
You mean?
Or which situation would be rather one over the other?
You mean the correlation coefficients or? Yes. So I would say correlation coefficients and linear regression, their purpose are different. For linear regression, the main purpose is to construct the functional relation between X and Y. So basically, we are interested about the exact relation between these two, and we may use one to predict another. So this is for linear regression, but for the correlation coefficients, we are only interested about the correlation between X and Y. So we do not use this one to do the prediction or to do any implications about their relation. So I think this is the difference. But I think according to my experience, many people, like many researchers, they may use the linear regression and they have the positive slope and they have the relatively large R square, and their conclusion will be they are positively correlated. I think like exactly this will not be quite valid, but I think because these are equal, so I think this statement is also correct. Yes. So any more questions? Nope. Oh, another thing I want to mention that for linear regression, X and Y, they are not interchangeable. Like if we change X and Y, then we will have different linear regression equation. But for the correlation coefficients, X and Y, they are equal or they are symmetric. If we change X and Y, the results will not change. So, does that make sense?
Can you say it again?
Yeah.
So for linear regression, like Y equals to AX plus B. And for another linear regression, we may change X and Y. So we may have alpha X plus beta. So alpha, like A and alpha, they do not equal. B and beta, they do not equal. So if we change X and Y, we may have different linear regression results in terms of this straight line. But yes.
The alpha and beta would be different values of A and B, but with the R squared still be the same?
I think the R square will be the same.
Yeah.
Yes. So any more questions? No. So that's all about the correlation. By having some analysis about correlation, I would like to talk about how can correlation applied in spatial analysis. But first, let's look at an example. So suppose we have 1D data. 1D data means that like this is like the distance, which is a spatial parameter, but we only have one spatial parameter, like which is the downward from a specific location. And suppose we measure PM 2.5 concentration from 4 sites. So for each one, we grab the sampler to 0 and work to here. So we can collect the PM 2.5 data in terms of the distance. And we have 4 sites. And for each site, we have different results. So for this 4 sites, do you guys think, is there any characteristics you noticed? Like for first one? For first one, I would say it is decreasing, like we have the decreasing concentration with distance. How about the second one? Oscillating, yes. So it like fluctuating and it has some periodic. And what's the third one? Kind of constant with some small noise. And for the fourth one, it is solely increasing. So we have like 4. Then we can ask up a series of questions about correlation coefficient. So what is the small r between CD and CD? So, and we can see D equals to 0, 1, 2, 3, blah, blah, and this is the same. So basically the concentration is a function of D. And the correlation between CD and CD means when D equals to 0, and here D also equals to 0. So the correlation between CD and CD means like the data, the correlation between the data and itself, because the delta D equals to 0. And then what's the correlation between CD and CD plus 1? When CD plus 1, we have a delta D equals to 1 here. So for this one, it still refers to when D equals to 0. But on this one, it's equals to D. The concentration at D equals to 1. And again, this is D equals to 1. This is D equals to 2. So we have like a shift. But note that because we only have like 21 data, so for this one, it is not available. We do not have data for this one. So we do not calculate this one. We only calculate the correlation between these 20 data sets. And again, between D and D plus 2. For D plus 2, delta D equals to 2. And then we have the column like this. And notice that we have 2 empty here. So we just ignore this 2 and we ignore this 3. So we can calculate like CD and CD plus 10, and also CD and CD plus delta D, and the delta D can be like 1, 2, 3 to any other numbers. But before, yes.
No, wait a second.
Yeah, okay, yeah. But before we are doing the calculation, I would like to introduce a concept which is called autocorrelation or autocorrelation function. I was trying to find any intuitive pictures from the internet, but I didn't find any pictures. So I just leave it here. I guess because this concept is a little bit abstract for many people. So for the autocorrelation function, it is a correlation of a signal, and this signal can be the concentration data with a delayed copy of itself as a function of delay. And in our example, the delay is delta D, and it can be 1, 2, 3, blah, blah, blah. So this is a definition of autocorrelation function. So do you still have?
I'll hold off until you have a calculation.
Okay. So let's look at site 1. For site 1, I'm not showing the whole process of the calculation. I just present the result with the scattered plot of the result. So this is the concentration change with distance at site 1. We know that it is like decreasing. And for the first one, this is CD, and this is CD plus delta D. And because delta D equals to 1, so this is the data of itself. And we can see they are on the perfect straight line. What?
Delta D is 0.
Yes, delta D is 0. So this is CD itself. So basically, we are plotting the data of itself as a scattered plot, and we can see they are perfectly on a straight line. And the correlation coefficient equals to 1 for sure. And then for the second one, when delta D equals to 1. So in this case, we still have CD here, but here we have CD plus 1 because delta D equals to 1. And again, we can also make this scattered plot, and we can calculate the correlation coefficient when delta D equals to 1. And the result is this one. And again, we can calculate when delta D equals to 2, equals to 3, equals to 4, and equals to 5. And we can see the pattern doesn't change a lot. Like all of the data are kind of positively correlated, and the correlation coefficients are around 0.9. And on the last plot, we have this plot of this is delta D, the delay or the lag, and this is R. If we make this plot, we can see when D equals to 0, the correlation coefficient is 1. And when as the delta D increase, we can see the autocorrelation, they just stayed in a relatively high level. Stay in a relatively high level. And so this is for site 1. Yes.
Oh, yeah, so I think this is, what exactly is D?
And D is a distance. Let me. So D is a distance of the concentration, or we can take a look at this. So this is our data. So at D equals to 0, we have a concentration. At D equals to another one, we have another concentration. And here D equals to the distance from a original point. Yes. Yes.
Could you go back to the last slide?
This one.
Is there a reason we stopped at 10?
No, we can do the calculation until like 20. Yeah, but here I just show 10 as demonstration. Yeah, we can do more, but here I just stop at 10. And then let's look at another one. So for site 2, we notice that it has like the oscillation or fluctuation with a certain periodic. And again, we can do the calculation with delta D equals to 0. Delta D equals to 1, 2, 3, 4, and 5. And we can see this is a little bit cute because this is a straight line, and then it's just open, and it's also extend again, and then it shrink on the other position, and it shrink again, and it's also open. So we can see it has some specific pattern. And if we summarize the correlation coefficients of each delta D, we can get this plot. And from this plot, we can see it also has kind of the oscillation with the data, with the correlation.
What is the lag mean?
The lag means, so the lag means we want to calculate so we have one data set, and then we want to calculate the correlation between the data itself and a delayed copy of the data itself, but for this one, your connection is unstable. So for this one, suppose we have the lag equals to 0, which means the CD equals to itself. And if the lag equals to 1, which means when D equals to 0, we pair this with when D equals to 1. And in this case, when D equals to 1, we pair this with when D equals to 2. So like we have two sets of data. Let's say we have a set of data like this. So basically, if we do not do the lag, it will be like this. But when we are doing the lag, it is kind of like we move this data going forward. So like they will have this correlation, but for this one, it will correspond to this one. Does this make sense? A little confusing.
Like I feel like the lag, like what is delta G? I feel like that would be the lag.
Yes, delta T is a lag.
So on the graph, it said delta D. I thought it said delta D minus lag, or maybe it was delta D, which is lag.
Yes, delta D is a lag, is a delay.
Yeah, if you go to the next page.
Yes.
Yeah, in the bottom right hand.
This one?
Yeah, does that say delta D minus lag?
Oh, this is delta D dash lag.
Okay.
This is not minus.
Okay.
Oh, I'm sorry for this confusing. Yeah, let's just ignore the lag. This is just delta D.
Yeah, thank you.
Yeah. Yeah, again, this is delta D. And it is also the lag. But yeah, it's minus lag. Okay. Yeah, I will revise this slide. Okay, anyway, again. So for site 3, we note that there is no big change, and it is kind of straightforward. If we are doing the correlation analysis, we can see they are just clustered or assembled in a very small chunk, and the correlation coefficients are relatively small, except for the first one, because it is a copy of this itself. We can see the R is very large, but for the rest of them, like the R is relatively small. And let's look at the last one. For the last one, it is solely increasing. And again, we can calculate the correlation coefficient in terms of each delta D. And we have this plot here. And this is pretty similar to the first one. Let's just go to the next slide. So we can see for site 1, which is solely decreasing, and for site 2, which is solely increasing, their autocorrelation function are the same or pretty similar. But for site 2, it has like oscillation. The autocorrelation function also has oscillation. And for this one, it has no change. And the autocorrelation has a very large value at the beginning, but it has relatively small value for the rest of them.
And for site 1, why were the R values not negative?
Because they are positively correlated. You can see if we are, because that is not about the value itself. That is about like the CD and this one. So if we are plotting CD and CD plus delta D, like they are all. So solely increasing and solely decreasing, they're the same, but these two are different. And in practice, I mean, the characteristics of these 4 sites is easily to be identified, and we can tell it by our eyes. But in practice, when we have something like this, do you guys think is there any special pattern of this data? No? So, but we can also calculate the autocorrelation function of this one. And the autocorrelation function is this. We can say this is beautiful, I think. We can see it has some oscillation. On the other hand, it's also like decreasing gradually. So in this part, so most of the data meaning of the data in practice will be something like this. Like we cannot find the characteristics of this data by our eye. So we can use the autocorrelation function to reflect some of the properties of this data. So here, I want to say autocorrelation function can reflect some hidden properties of the data. Yes.
Can you go back one slide?
Yes.
Why was the site 3, the autocorrelation so random?
Yes, you can. Because when we are doing the data analysis, we can see the data itself and the data with the lag, like they are all clustered. So for this cluster, there is no obvious trend. So the correlation coefficient is very small or relatively small. And again, for this one, we can see from this plot, we can see this is a combination of them. We have the oscillation, we have the large correlation, we have the small correlation, and we can see it also has the oscillation. It also has a large correlation, but the large correlation is gradually decreasing. So it is a combination of the characteristics that we observed from before to this one. And so the temporal or spatial characteristics of the data can be reflected by the autocorrelation function. So these are two take-home messages. So for this one, do you guys have any questions? No? Okay, so this is only 1D data, but in practice or in spatial analysis, we usually have 2D data. Like we have data of X and Y. So for 2D data, it will be more computationally intense. So first, we want to find the pairs of given distance. For 1D data, we only consider like at one direction, but for 2D data, we also need to consider the direction of this distance. So actually, we want to find like this is 1 meter, like any point that is 1 meter away from this one point. So like we can find many pairs, like 1 meter, 2 meter, or 3 meter. But again, we need to consider different directions. So we can see that the number of pairs increased significantly or substantially. So I'm not going to ask you guys to do this calculation. I just want to show the concept. And then we calculate the correlation coefficient with different delta D. So again, we are not going to do the calculation, but here I want to show some concept. So for 2D spatial analysis, we do not usually use correlation versus lag distance or delta D, but we use the variance or covariance versus lag distance. I think this is because of the transition. Like the original paper, the original researcher, they just looking at the variance versus distance. So I think this is just a transition. And here is a definition of correlation function. And this is a definition of covariance function. Again, we are not doing the calculations, but for the concept, intuitively, we can see. So for most of the situations, the correlation is decreasing with the lag distance. Like if we are very close to each other, it is very possible for us to have a high correlation. But if you get away from me, then our correlation will decrease. So let's describe this relation. And this relation is described by the correlation function on the left side. And we can have the number A. The number A represents the situation that when you are far away from me, which is larger than number A, then we are totally uncorrelated. Then I have no influence on you. So we know that the correlation decreasing with distance. And then for the covariance function, we can say we just use a constant minus the correlation function. So we just use a constant minus this one, we can see this will be something like this. So this is the shape of covariance function. And again, we have an A here. And we can see the covariance just increase up to a maximum value. And then for the correlation function, intuitively, we can see that the variance between us increases with distance. So if you are going far away from me, it is very likely for us to be different. But if you are close from me, the difference between us will be relatively small. But in spatial analysis or in geostatistics, they do not use this one. They just define this one as 2 times gamma, and they use the gamma versus the distance instead of the variance versus the distance. So again, I think this is a tradition of their processes, and they call this variogram or semi-variogram because it is half of the variance. So again, you just need to understand the concept. You don't have to remember the equations. So for this one, do you guys have any questions? I guess I will have an example here, which makes it more intuitive. So these are the pictures that I show on the water chemistry lecture. This is a sea level alkalinity. We can see it is like this. So suppose we are standing here, which we have relatively small alkalinity. So if I'm here and I look around, which for a relatively small distance, we can see that the alkalinity around me are also supposed to be small. But if I walk around at relatively large distance, we can see it could be high, it could be small, it could be high. And if you make this like even larger, so again, it could be high, could be low, could be high, could be low. So the variance increases. So intuitively, it will be something like this. As the distance increases, the variance of the alkalinity between me and that place will increase. And this is the same for this one. So for most of the environmental data, they have this relation. And so for this one, you guys have any questions? And so for the variogram, like for the variance versus the lag distance, we know that it will be something like this. But in practice, how can we get the mathematical expression of this one? And so in practice, we use the curve fitting. So we have some different functions, and then we can use our data. We can use this model to fit our data. And we can see, although it looks like this one, but we have different variations. Like we just start from a very large value, we can consider it as the limiting condition when A equals to 0. Then it will be something like this. And then we have different shapes. And if the data is fluctuating, we know that the correlation, autocorrelation function is something like this. But note that this is start from 0 or start from 1 for the correlation. So for the covariance, it starts from 0, and it can also have some fluctuations. And this one is a combination of different effects.
Is this still something that only applies to the 2D data, or we make variograms for 1D data?
This can be used for 1D and 2D and 3D. Yes. Yes.
Are we changing A here?
Yes, the A can be different. And in this one, it A maybe something here. And for each of the curve, it has its mathematical expression. I do not display them here, but the A is evolved in the expression.
But are we defining the A, or is it calculated by the data?
Yes, when we fit the data with the model, and then we can use the parameter of the model to derive A or calculate A. Yes. So any more questions? And the next one is about how to interpolate spatial data. So in most of the situations, we are doing the observation at different spots, and then we will have the data like this because we cannot observe the data at every places. So the question is, we want to interpolate our data, like we want to know the concentration of like CO2 concentration at everywhere. So we want to have this result. And this process is called mapping. And so the method we are going to use is spatial interpolation. So spatial interpolation is a type of estimation and a method of constructing or finding new data points based on the range of a discrete set of known data points. So basically, the known data points are usually limited. And we have two types of methods, deterministic methods and statistical methods. For the deterministic methods, we have inverse distance weighted methods, natural neighbor interpolation methods, and spline methods. For the statistical methods, that is a Kriging method. And because of time, because we are not going to do the calculation, I may ignore some of the text. I will just avoid reading some of them. But for the nearest neighbor interpolation method, and it is displayed here. Suppose we have the data point here. So basically, we just find the middle line of these two data, and then we make the vertical line. And we can do this for many times. And for each of the data points, it can be included by a polygon. And then we assume the concentration of this polygon equals to the concentration of this data here. And so, yes. And then, so for this method, it is relatively simple. So it has the advantages of it is computationally cheap, and it has a ability to preserve original values in the unaltered things because we do not change any of the concentration data from our original sample. But it also has some problems. So it has the position errors. We can see it depends on the location of our sampling point, and it is also a non-smooth interpolation. We can say we have a sudden change of the data from this boundary line. Do you guys have any questions? No. The next one is an inverse distance interpolation method, a weighted method. So this method assumes that the variable being mapped decreases in influence with distance from its sampled location. So basically, suppose we have the sites and we know the concentration of X1 up to X6, and we want to know the concentration of X0 in the middle. So this X0 is unknown. So we want to know the concentration of this X0. I just use Z hat to represent this. So basically, we are going to calculate the weighted average. So this is a weight of the first known sample, and this is a value of the first known sample. This is second, and this is the nth. And then we add the weight together to normalize its value. So basically, we are calculating the weighted average of the sample of the concentration of the samples from each location. But the point is that for the weight, we can use this relation. So H represents the distance between X and Xi. We know that for different points, the distance will be different. And we also have a P, which is a parameter. And in this one, the P is usually equals to 2. So by knowing the distance, by knowing the position of each sampling point, by knowing the P and knowing the Z value or the concentration at each point, then we can estimate the concentration of X0. And here shows an example. So with different p-values, and we can see the interpolation results are different. So for this one, do you guys have any questions? No? Okay, I guess I may just use extra 5 minutes. And here are pros and cons of the inverse distance weighted method. It can estimate the exchange changes for different places, and it can dense evenly spaced points are well interpolated, and it can increase or decrease the amount of sampling points to increase the cell values. And it also has some disadvantages, like it cannot estimate above maximum or below the minimum value because it is the weighted average. And it is not very good for peaks or mountainous areas. Because it's only consider the distance, it does not consider the geographical changes. And the last one is the statistical interpolation method, which is kriging. And here I say this is ordinary kriging because we also have some other kriging methods like the universe kriging or like simple kriging. And ordinary kriging is the mostly commonly used method in spatial analysis. This slide is a little bit colorful, but again, we are not going to do the calculation. So based on the inverse distance method, we know that we can have some weight times, like we can calculate the weighted average of the concentration of the sample. And this is a weight, and this is the value. And in this case, we can just normalize the weight into lambda. So we can have the lambda, which is a normalized weight, or we can consider it as a weight, times the concentration or the value of each sample. So again, this is also a weighted average. But in kriging, we add some constraints. So first, the sum of the normalized weight is equal to 1. So this is to make sure our estimation is unbiased. And then this lambda or this weight is a function of the correlation function. So and we know that, like intuitively, we can see if we have a larger correlation between us, then the weight will be larger. And then we also have this semi-correlation function or variogram relation, like we have already constructed here. And here shows the variance of estimated value at x0. So the variance can be expressed as this one. And everything on here is known. We may say the true value as x0 is unknown. But if we are opening the brackets of this mass expectation, we will have the expectation of x0, which equals to mu x. So like we have these 3 equations here, and then we want to find the lambda i's, like we have different lambda i's as the weight to minimize the variance of this estimated value. And then we can solve these equations, like this is an optimization problem. And then we can calculate and we can solve for different lambda i's. And on the left side, I just want to show, because it depends on the correlation function or the variogram. And for the variogram, we have different models. So if we are using different models to fit our data, the results will also be different. So again, the results depends on the model that we choose. And so I think this is the last slide. So for the same data, we have the distance, and this is a semi-variogram. We can see the variogram looks like this. And then this is the interpolation result. And for kriging, it has advantages that it provides the measure of error because we express the uncertainty or standard deviation of the estimated value. But the disadvantage is that it is computationally intense. We can see the formulas are creepy. You guys have any questions about kriging?
Does this also like the inverse distance, does it like assume that the concentration decreases as
The distance.
delta D increases?
You mean for kriging?
Yeah.
From this plot, so yes, because for this plot, we can see the variance increase as the distance increase. So the correlation decreases as the distance increase.
Yeah. Okay.
Yes. But for kriging, so first we need to construct this variogram. So it can give some general ideas about the correlation between the difference and the distance. And by putting all of these results together, we can see that by using different methods, we can have different spatial interpolation results. And even by choosing different parameter values, we can have different results. So the conclusion is that the spatial interpolation results are method dependent. So if we are doing this research, we need to be carefully choosing the methods and the value of the parameter. And that's it. But finally, I want to, here are some notes for 411 assignment. I just added it in the morning. So basically we do not have lab reports. We just have the group assignments. And so in the assignment 2, in general, I would say the uncertainty can be expressed as standard deviation. But in practice, uncertainty can be expressed by standard error or the confidence interval and some other values. But in this assignment, we can just consider uncertainty equals to standard deviation. And for question B, the signal is unitless. We do not care about its unit. And the uncertainty of the signal, again, we can use standard deviation to describe this. And for question C, we have H, the mercury extraction. So we can just assume the mass is balanced or the mass is conserved. So all of the mercury in the soil sample is transferred to the solution. And for question E, it says the average of 4. For this one, if you guys are doing this question, you can just ignore the standard deviation of this average measurement of the 4. And that's it.